In this video, we are going to cover E4, that is fission. In nuclear fission, it is a process where a heavy nucleus splits into two lighter nuclei. There can be two types of fission. There is an induced fission, which we artificially create by bombarding neutrons to the nucleus. And then there is a spontaneous fission, where a nucleus splits into a smaller nuclei without any intervention of external neutron. Okay, so what we are going to focus more on is the induced fission, because that's how we create nuclear fission energy from it. And you can see an example of reaction of induced fission, where you can see how neutron is bombarded on a uranium atom. Uranium atom then absorbs that neutron and further splits into a barium and a krypton nuclei, and simultaneously releasing 3 more neutrons. And also in spontaneous fission, you can see that a neutron is ejected in this fission. So ejection of a neutron is very characteristic or key feature of a nuclear fission, and we are going to see how we can extract energy from those ejected neutrons. Okay, so if we control this energy that is released in this reaction, we will make a fission reactor. And if we don't allow that energy to be released in a controlled way, in a very short time, it will act like a nuclear bomb. Now, nuclear fission reactor, to understand nuclear fission reactor, we will start from very basic. Like if we are mining uranium, there are a lot of problems with uranium mining, because it is radioactive. It can harm the people who are mining it. All those things, controversies are there. That's the reason why these are one of the disadvantages of nuclear fission. But there are a lot of advantages as well that we will discuss right now. But if we have a uranium ore, it will usually contain uranium-238 and uranium-235. Uranium-235 is an isotope of uranium, and that isotope undergoes fission readily. Okay, when we bombard neutrino under it. Now that is very small percentage of the original amount. So if I have a uranium between, not all the uranium is going to have the ability to undergo a fission reaction. Okay, so only uranium-235 has, and let's say I bombard a neutron onto a uranium atom. So first of all, the size of the nucleus is very hard. Atom is mostly empty. When we saw Rutherford scattering experiment, we saw that there has to be a lot of alpha particles that's to be sent, out of which few will deflect or had a head-on collision with the nucleus. Similarly, here also neutron, we don't say one single neutron, but rather a beam of a neutron that will eventually, one of those will hit the nucleus of a uranium atom. Now this neutron has to have certain energy to get closer to the uranium nucleus, and then it gets eventually absorbed. So uranium, the nucleon number will increase, and here you can see that this is an example. So uranium does not only always split into barium and krypton; it can go into xenon and strontium also. So there are different combinations of nucleus. It splits. Now, what is the one key feature about those nuclei which are product of splitting of uranium is that the product nuclei, whether it is barium or krypton, or it is xenon or strontium, product nuclei have higher binding energy per nucleon than the uranium. So if you look at the binding energy curve, as the heavier nuclei, the binding energy per nucleon decreases. So whenever it breaks, there is a nucleon of higher binding energy per nucleon is raised. That's the reason why even the fission can cause a release of a lot of energy. Now, the main key feature is those neutrons which are released in this reaction will collide with other uranium atoms, and then further make them split out, and it will start a chain reaction. So this is a self-sustaining reaction where one reaction provides the fuel for the another reaction, and more energy and more neutrons are released in a short span of time, which creates, as I mentioned, a nuclear bomb. If it is not controlled, if it can control this energy, it will be reusable. Okay, and this chain reaction, for the chain reaction going on, there is a minimum mass of uranium-235 that is required to be present, so that the neutron does not escape without creating further reaction. So that minimum mass is basically what we call as critical mass. Okay, below critical mass, what happens is there are not enough uranium atom in that false confined phase that a nuclear reactor chain reaction is sustained for a long enough time. Okay, now we will talk about one of those reactors. So there are two kinds of reactors. There is a gas cooled reactor and there is a pressurized water reactor. The only difference is the moderator, and we will talk about what is a moderator. So first thing, that uranium-235 will only capture the neutrons if neutrons are not too fast, because if they are too fast, they won't be absorbed by the uranium-235. So the slowing down of the neutron is achieved through collisions of the neutron with the atoms of moderator. Moderator is a material that is surrounding the fuel rods. So fuel rods, you can see in the diagram, there are black lines which are fuel rods, and those fuel rods basically are surrounded by the solid material in this diagram, which is a pressurized water. So water acts like a, a moderator, but apart from pressurized water, the other variant is gas coolant, where we have graphite, solid graphite surrounding the fuel rods. Okay, and fuel rods, as we know, it is made up of uranium. So those are the moderator, which is whose job is to slow down the electron. Now, after slowing down with, because through the collisions, their job is to take this energy and make it transfer to other system where that energy is converted into some usable forms, like heating the water to convert that into a pressurized steam. So then that's required, like a heat exchanger or some kind of that system is required, where heat is extracted from the moderator by circulating cold water from the below, and then that heat is transferred to some other system where the water is heated and turned into a steam at high temperature and pressure, and that steam is allowed to rotate a turbine which generates electricity. Okay, so this is the mechanism of how the energy is created, okay, from the nuclear fission. Now, this fuel rod needs to be controlled. We need to control those reactions. So that's why we have control rods. Now, control rods basically absorbs the neutron and can be raised and lowered down between the fuel rods, so that what happens is, like, those neutrons. So sometimes we want to stop the reaction or reduce the rate of reaction. So we can, depending on how much reaction rate we want, we can adjust the height of the control rod, and thus prevent too high reaction quantity, rate of reaction, or too low rate of reaction. So we can control the rate of reaction using control rod by inserting them or removing them. Okay. So these are the few important. What are the control rod made up of? So ideally, the control rod are made up of boron, but there are some other variants also that can absorb neutrons. Now, what are the energy of the power of a nuclear fission? Yes, it is a high power output, because a small fission, very small amount of uranium can create a lot of energy. Okay, which is like tremendously high compared to the energy that we extract from burning coal and fossil fuel. Then we have large reserves of nuclear fuel like uranium and plutonium. We have that. Again, those nuclear power stations do not contribute any greenhouse gases, so that is also an advantage for using a nuclear energy. Now, what are the disadvantages? The disadvantage is that the nuclear waste that is generated, usually those confinements, those systems, the fuel rods and everything is confined under very large, thick concrete, so that any kind of a radiation leaks are prevented. But the radioactive waste product, it is very difficult to dispose. So we usually dig very underground tunnel or underground bunkers where we store all this radioactive waste. Also, major public hazard is possible if something goes wrong. And we have example like Chernobyl, where there was an explosion, not explosion, we would say meltdown of a core because of the uncontrolled conditions. And there is also problem associated with uranium mining, possibility of producing material for nuclear weapon. All those things are probably the disadvantages of nuclear fission. Now, in this chapter, this is a very short chapter. First of all, we need to understand. So what we will try to do now, we will try to answer a few questions related to this chapter. In nuclear fission, a nucleus of element X absorbs a neutron and gives out element Y and element Z. Okay. The magnitude of binding energy of Y to X has to be greater than 1. As I mentioned, the binding energy for the nucleon is greater, binding energy per nucleon. So this is obviously greater than 1. Okay. And total binding energy of X and Y upon total binding energy of X. Now, in this scenario, total binding energy of X upon total binding energy of X has to be greater, because there is a energy released in this reaction, and most of the energy released is taken away by the neutron. So correct answer is 8 here. Okay. Then we have in the nuclear fission reaction, nucleus splits into nucleus Y and Z, which are the following in the order of lowest to highest binding energy per neutron. So the lowest will be X. Okay. Now the nuclear number is not here, but the Y, it's Z and Y both will have nuclear energy. So you will see that in this most of the reactions that we, let's say for this example of barium krypton. So you will see that there is a higher number of binding energy per neutron for barium compared to krypton because it has a lower number of nucleon. Okay, that is 89. So binding energy is a higher for this barium, and krypton has the second highest, and the least will be for the uranium, like that. So this kind of comparison is done. Then what do you mean by binding energy? Yes, binding energy means energy required to bring form a nucleus from the individual nucleons. Now see, binding energy for the nucleon for each atom is given. Now, outlying the quantities such as atomic mass and nuclear binding energy are often used in non-SI units. Yes, because it is convenient. We can't write everything in 10 to the minus 27 or 10 to the minus 19. So it is much more convenient. Shows that the energy release is 180 mega electron volts. So this is something that we can do. Energy released is usually taken by, we have to find the binding energy first. So let's say this is the binding energy per nucleon. So we will multiply with 235 to get the binding energy of the uranium. For Xeon, it is taken like 140. We will multiply this with 94. And we don't have to take the binding energy of the neutrons. So take the binding energy of the products minus binding energy of the reactant, and we will get the answer. Now, the main question is, the nuclear power station has a few, every reaction is releasing 180 mega electron volts. Now, what is the specific energy of the uranium-235? Now, specific energy is nothing but energy release for 1 kg of the fuel. So energy release for 1 kg of uranium. So first I need to figure out what is the number of atoms present in 1 kg of uranium. So we know that mass upon molar mass is equal to number of atoms upon Avogadro's constant. The number of atoms would be mass upon molar mass into Avogadro's constant. So mass is 1 kg, so I will write it in grams, that is 1000 grams, and molar mass is 235. And then we multiply this with the Avogadro's number, 0.622 into 10 raised to 23. Okay, now this number will turns out something, but now this is the how many uranium atoms are present. Now, if one reaction required one uranium atom and that releases 180 mega electron volt, we want our energy released in joules. So energy released to be 180 into N that we figured out from here, and that is converted into mega electron volts to joules. So 10 to 6 electron volts is 1.6 into 10 to minus 19 joules. We will get our answer in joules. Okay, that is a joule in for 1 kg of uranium atom. Okay, so this is how we calculate the energy release. Now the question is asking again that how many mass of uranium-235 is required to undergo fission in 1 day if the efficiency is 36 and the power output is 1.2 gigawatts. So power input, first we can figure out what is the power input that is generated from fission of the uranium. So that would be 1.2 gigawatts upon 0.36. So that will give me some number. So 1 gigawatts is 10 raised to minus 9, and this is 0.36. Okay. Now apart from this, now what is energy power? Power is basically energy release. If it is measured in watts, but it is basically energy release per second, because it is watt in joules per second. So energy release, it is per second. So in 1 second, this much energy is released. So how much energy we can release in 1 day? Okay, so we can calculate that energy released in 1 day, and that will be this number, that is 1.2 into 10 raised to 9 upon 0.36 into 1 day. So 1 second is releasing this much energy. So 1 day is like 60 seconds, 60 minutes, 24 hours. So this will give us a certain number, and then we can calculate the mass required to release this energy, because we know that energy released in 1 day, 1 kg is how much. Okay, so since we know energy released in 1 kg, we will divide that energy per kg. We will divide this number with the energy required in 1 day. Okay, and then we will get the mass required to this in kgs. So this is how we do the problems of nuclear fission as well. It is very simple to the energy problems and whatever the problems that we did in nuclear physics, that is E3. But this chapter is very simple, straightforward, and there is nothing complicated here. All you need to remember some basic terminology related to nuclear fission and nuclear fission reactors. Thank you.